First of all, we are so sorry not to be there in person. We really, really wanted to come, but we ran into childcare issues, and I'm so jealous that you've been on a hike. We're both mountaineers, and so we really feel we've missed out by not being there in person. The venue looks fantastic, but it's been really, really grateful about what a great connection you've given us to be able to listen to everything on Zoom, record all the talks. So thanks so much for all of the efforts you've been making. I'm a cosmologist, so I'm going to talk about cosmology, and really, I think just give you, my goal is to give you a flavor of what we do in cosmology and how in different ways that connects to ideas about determinism, indeterminism, quantum processes, and other things like that. And hopefully, by giving you that picture, it will raise a bunch of questions. And certainly, by the time we get to the end of the talk, I have a whole bunch of things I'd like to know better, which are more suggestions for thinking and discussion than me telling you something that I think I really know is true.
Excuse me, Andrew.
Yes.
We have some echo with the volume here. Maybe it's better.
Can't we use that microphone or not the microphone?
Okay.
We should be able to.
Your app is running and can access the internet.
We tried that a bit and it wasn't working, but in principle we should be able to. Yes.
Or even here in the book, probably there is a speaker here. No, the speaker is the other one that the mic is in his hands, or the TV, or the computer itself.
That's already what we're using.
Yeah. But this the speaker cannot go onto the.
It should be able to, but it doesn't. We haven't been able to get it to work.
No, yeah.
I'm not sure whether I can continue or whether you need to do something to the sound. Let me know.
I think it's not too bad with that TV sound, but
okay, I'll proceed then. So I want to tell you things about how we do cosmology and try and give you a picture of.
Say something, Andrew.
Yes, I'm happy to say something. Yes, I think I'll proceed, and if things are not working well there, just let me know and I'll stop and we can.
It's fine now, Andrew. Thanks. Sorry.
Okay, perfect. Thank you very much. So the first thing I want to tell you about is the ingredients that we typically use in modeling cosmology. We're trying to deal with the universe as a whole. We need to build models to do that. So how do you consider cosmology? I think the starting point is always ideas. You want to have some ideas about what you want to describe. So obviously the hot Big Bang cosmology is the basic framework. We want to understand things like galaxy and structure formation that Mark has already talked about on Monday. One of my personal interests is understanding how the universe behaved when it was very young. And one of the concepts I'll be talking about today is inflation in the early universe and how that impacts on ideas of determinism and indeterminism. But these are basically the ideas, the framework that we're going to try to use to understand the universe. So once you have that big framework, your next goal is to figure out what are the actual physical laws that you need to bring into play. What are the relevant parts of physics? And cosmology has a lot of these. It's largely driven by gravity, for which general relativity is our best theory. But for different parts, you have to bring in a whole pile of other physics, particularly atomic physics, nuclear physics, particle physics, because we're normally describing individual particles and their interactions. Neutrino physics can be important. And as we'll see from time to time, you also have to consider quantum mechanics as well. And perhaps on the grandest scale, you have to consider the effects of quantum mechanics. Clearly, when quantum mechanics is introduced, we may be making a switch from a purely deterministic setting, as in the Newtonian type of framework, into one where there is also randomness superimposed on that determinism. Once you've got your laws, you have to go through a whole pile of mathematics, because the goal of all of these physical laws is to try and find equations that let you describe observables. We're going to be going out and measuring things. The things we measure will be actual numbers. There will be intensities of radiation on detectors, other things like that. And so we need quantitative predictions from our theories in order to try and match them to observables. It turns out that to do this, you typically need some big computers because the calculations are complex. The physical laws are themselves not very complicated, but the environment in which you want to understand their implications can be complicated. So cosmology in some ways is like a big weather forecasting problem where you're trying to understand environmental effects of different kinds. Then we need to understand what the universe is like. And the big transition during my lifetime as a cosmologist is the existence of massive data sets to show us what the universe is actually like. When I started out as a PhD student, essentially there was almost no data at all. Vague ideas about how fast the universe was expanding was about it. But nowadays we have precision data sets, which are gigabytes or terabytes in size, that give us very detailed pictures of different aspects of what the universe is like. And so we're compelled to make theoretical predictions to high precision in order to match them to these data sets. Finally, something I've spent a lot of time on in the last decade or two is we need very refined statistical methods to compare our models to the data and try and figure out what the parameters of the models are. So all of these ingredients are the day-to-day working ingredients of a cosmologist. And the end point is to try and understand something about our universe, such as, for example, the relative amounts of different material. The current view of the content of the universe is that there's about 5% of the normal matter, atoms, radiation, electrons that we're made of. Big chunk of dark matter, which is responsible for the gravitational attraction that forms structure, holds galaxies together. And then an even bigger chunk of dark energy, which is responsible for the observed acceleration of the present universe. The expansion rate is increasing with time, as is measured to quite high precision. So to give you a view of the sort of thing I have in mind here, this is a mission I was involved in, the Planck satellite mission. You can see from the timeline, satellite missions are very long things. It ran for about 25 years from being first thought of until it finished a few years ago in 2018. This particular satellite was working in the microwave band, measuring the cosmic microwave background from a position about 1.5 million kilometers from Earth. It's a European Space Agency project. And the purpose of that is to build a large data set to let us understand the distribution of radiation in the universe, and the radiation is tracking the distribution of all the other kinds of matter as well, if we interpret that in a cosmological model. So the sort of data set you get from that is this. This is an all-sky map of the cosmic microwave background. So you have to imagine that the radiation is emanating on the surface of a sphere around our location, and that sphere has been flattened onto the screen. So we see this sort of elliptical structure. The galactic equator lies along the horizontal axis in the middle. And Planck gives measurements of approximately 10 million pixels on the sky. So you can see the temperature measured in variations of microkelvin about the mean temperature given by the color scale. You may know that the mean temperature of the microwave background is about 3 Kelvin. So the color scale represents fluctuations in temperature of only about 1 part in 10 to the 4 at most. Typical fluctuations are actually about 1 part in 10 to the 5. So the cosmic microwave background is extremely uniform, but you can see really lots of detail measured that show it's not precisely uniform. And these are the irregularities which later on will develop under gravity and lead to the formation of galaxies, the clustering of galaxies, and other things like that that Mark's already talked about at this meeting. Now, in terms of understanding our universe, the cosmic microwave background has for 20 years and continues to be by far the most important source of information, because it's very well measured, and it's also relatively easy to interpret as compared to other kinds of data that we can get in cosmology. So I tend to focus a lot of attention on that. So what do we do with this data? We create a model of cosmology, and the standard model of cosmology depends on 6 parameters. These are the things we're trying to measure, like the densities of different kinds of material. I'm not going to labor what the parameters actually are because I don't think it's very relevant to the question of indeterminism. But just to show you roughly the kind of data fits that we have, on the bottom left, you see a plot of the power spectrum of the variations. So we have the temperature variations are on the surface of a sphere. You can write them in terms of spherical harmonics and ask what is the typical amplitude of the fluctuations for different harmonics. The x-axis here is the spherical harmonic index L. because there's about 10 to the 7 pixels, the L range is the square root of that. So there's a few thousand independent measurements corresponding to different scales, the largest scales on the left, the smallest scales on the right. And what you hopefully see is that the data is measured, the spectrum is measured with very high precision. The error bars on the right-hand side are mostly much smaller than the size of the point that's being used to represent them. And the lower panel shows the residuals of the data against the best model fit, which is the blue line running through the data. So the blue line is the theoretical prediction of what the microwave background should look like given particular values of cosmological parameters. And because the error bars are so small, you can measure the cosmological parameters to extremely high precision. And the measurements are shown on the right-hand side here, but the only thing I invite you to look at is that the error bars on all of these measurements, for example, the top one is the baryon density of the universe, the error bar is exceedingly small compared to the value that's being measured. So we have very high precision measurements of properties of our universe using data like the cosmic microwave background. Why are there 6 parameters? It's really a property just of the data set we're choosing to fit. You have to decide how many different kinds of physics might be relevant to the kind of data you have in hand. If you want to measure the cosmic microwave background, it turns out you need to vary 6 parameters. The densities of the different kinds of material are important, the baryons and the dark matter. The expansion rate of the universe is important. And also the nature of the irregularities of the universe, what you assume about the perturbations in the universe, the variations, is important. But turns out it can be modeled quite simply. And normally we just use 2 parameters to do that, an overall amplitude and a scale dependence, assuming a power law form for how the initial power spectrum varies with scale. Again, I'll turn back later to some further motivation for that. So in this case, 6 parameters fit the data. And this, it turns out, lets us fit essentially all the major data sets we have in cosmology. I'm just showing you one, but there are many different kinds of data, measuring things like gravitational lensing, the clustering of galaxies, the expansion rate measured by supernova, etc., etc. And this works beautifully well, as I think you've already seen from these pictures. So the current status of observational cosmology is pretty fantastic. Precision measurements of essentially everything that we want to know about the universe. I'm not an observer, however, I'm a theorist, so I'm more concerned with the status of theoretical cosmology. And there are the pictures, almost the diametric opposites to the one we get from observational cosmology. For example, we've measured the density of matter in the universe to 1% accuracy. From a theoretical perspective, we have absolutely no idea why the universe is all matter with no antimatter. Observed to huge precision, no theoretical explanation at all of how much matter there is in the universe. We've measured the dark matter, I have no idea what it is. We've measured the dark energy, and we have no idea what it is. And we've seen good evidence that the universe has this rapid expansion, inflation during its early stages, and we have no idea how that took place either. So from a theoretical perspective, we are very far behind the observational modeling, which is essentially a phenomenological modeling of the universe, which is very successful. The gap is relating that phenomenological model to a fundamental understanding of what the contents of the universe are and how they interact. This is the same thing just said with numbers rather than just words, that the 6 parameters are shown here. They're the top 6 lines of this table. The measured accuracy in many cases is 1%. So the error bar just 1% of the size of the value being measured. In some cases, it deteriorates to about 10% or so. But the theoretical accuracy listed on the right is, our best predictions of these quantities is typically orders of magnitude, or we have no way to explain it at all. There's only a couple of parameters where there's some kind of reasonable distinction. What happened there? On the other hand, all of this framework from fitting the theory to the observations tests a wide range of physical laws that we're using to do that. So down at the bottom of this table, you see that we have the different types of physical theories we're going to deploy. Atomic and nuclear physics are tested to very high precision. And neutrino physics is not very well tested in the laboratory, but the universe is full of neutrinos and we have to incorporate them to make our models. And so we learned quite a lot about neutrino physics that way. Gravity, cosmology is one of the key tests of gravity. We use general relativity and no one has ever seen any violations of general relativity in analyzing cosmology. People are always hoping that they might, and one of the possible models for the dark energy acceleration of the universe is that it's actually a gravitational phenomenon, some deviation from general relativity. But we know general relativity holds very well for most of the evolution of the universe. Otherwise, our predictions would not match the observations well. And quantum field theory is also mildly tested insofar as the theory of inflation is a good model of what goes on in the universe. So I want to develop this and discuss the different kinds of explanations we're using in cosmology and try to relate that to the questions of determinism and indeterminism. So I'm going to go through quite a few steps of this. So just to restate again, the main observables we tend to be dealing with are the development of cosmic structures. So one way to view this is that the cosmic microwave background is telling us what the young universe was like. This is from a time of a few 100,000 years old, and tells us that the universe was very evenly distributed at that time. The density variations are only about 1 part in 10 to the 4. But the present universe looks very different from that. And you've seen in simulations, Mark again showed examples of this. These are simulations that show roughly the structures. In the left-hand side, you see the dark matter distribution predicted in a typical cosmological model from the Millennium simulation. On the right-hand side, you see dark matter on the left is the blue, and then just graphically the distribution of normal matter, baryonic matter, atoms and things shown in orange on the right. This is a kind of composite picture that shows the difference between the two. From the illustrious simulation, the universe has evolved to become very inhomogeneous since the time of the cosmic microwave background, and our strongest tool in understanding cosmology is to model that evolution and figure out how you get from the very smooth initial conditions due to gravitational attraction to develop precision predictions for what the distributions of dark matter and other things look like in the present universe. So that's the basic tool. Now, how do we do that in terms of equations? To evolve the cosmic microwave background up to the present, we're invoking deterministic physical laws, so classical physics. And the way this is done is that we model with using general relativity for gravity, and we use a fluid approximation for each kind of particle. So there's a fluid describing the energy distribution of dark matter as a function of position and time, a different fluid describing the baryon, a different fluid describing the radiation, different fluid describing the neutrinos, and everything is modeled in that way through a set of equations. Or when the perturbations are small, it can be modeled by linear equations, sometimes called Boltzmann equations. When things develop more, you have to do simulations to incorporate the gravitational collapse. But it's all classical deterministic physics, which is being used to get from early times to late times. But on the other hand, the initial conditions that are used are randomly chosen. They're not deterministic. Now, the way it's set up normally in a cosmological simulation, such as the ones I showed on the last slide, is you set up a large periodic box of whatever size of the universe you're trying to simulate, and you insert waves into that box, which are the perturbations which are representing the kinds of structures we see in the cosmic microwave background. But the amplitudes of those waves are chosen randomly, and they're drawn from a Gaussian distribution, usually, because that's what the data tells us the distribution looks like. And with a power spectrum, which is not specified exactly, but rather has to be determined from the data. And a simple model for that power spectrum, as I said before, is a power law, where you have to specify an amplitude and a scale dependence. And by varying these, you can try and constrain them and find out what values are best fit to the observations. So this is a sort of a mixture of deterministic and random in making these models. Another comment which I think is relevant to some things that were said earlier is that On the largest scales, and in particular on all of the scales needed to predict the cosmic microwave background, the perturbation equations are linear perturbations. The perturbations are small, they're growing under gravity, but they're much, much less than 1 and can be approximated by linear equations. And what that means to me is that for most of cosmology, there is no complicated physics going on. There's no nonlinear evolution, there's no mixing of trajectories, there's no chaotic phenomena on almost all scales of cosmology. And it's only on the smallest scales where galaxies are forming, which is what, again, Mark was talking about on Monday, that you have nonlinear phenomena, radiation feedback, and other things like that. Now, what you want to do is get a vision of how big the universe is for this. The observable universe, which is from where the cosmic microwave background originates, more or less, it's been traveling for the entire history of the universe, so we see right across the universe to it. The observable universe, which is the region from which we can receive light, is tens of gigaparsecs across, whereas the non-linearity scale is a few megaparsecs, so a difference of a factor of 1,000. So to visualize this, just look at the computer screen in front of you. You imagine the universe is the whole computer screen. You have some waves or perturbations of some kind across that computer screen. The scale of non-linearity is the scale of an individual pixel being displayed on that computer screen. Every scale bigger than a single pixel can be described using linear equations and is not subject to any complicated phenomena. I think that's important to understand and is a serious limitation for believing that the cosmos has any capability to moderate itself or feedback on itself. Now, these random initial conditions, what's that about? This is important, I think. When people first started measuring the development of structure, I think that this randomness was just because people would say, we have no way of accessing the initial conditions. We know nothing about the initial conditions. If you want to do a calculation, you have to assume something. So we have to assume some random perturbations that are going to set structure formation going. Later on, you could say instead, this is not something inaccessible. Once we'd measured the cosmic microwave background around the early 1990s, it could be taken as an observed property that the initial conditions are random, because you look at the cosmic microwave background and you see that that's what it looks like, and you can take the properties of the cosmic microwave background as a kind of initial condition to be evolved forward to give you the structures we see today. So the randomness is, in this case, observed rather than theoretical. But things changed again a bit in viewpoints during the 1980s, because we had a theory, this theory I keep mentioning called cosmic inflation, which is a theory of the initial conditions for structure formation. In inflation, the universe undergoes a very rapid period of acceleration when it's very young. During this period, quantum effects are important, and the quantum effects give rise to these waves, the initial conditions, the inhomogeneities in the universe. And so in this picture, there's a theory of physical origin for the perturbations, and they are random because they are quantum processes. And so the randomness is now viewed as an intrinsic property of nature, that cosmology can only be understood within a quantum universe. And if there weren't these quantum effects, there wouldn't be any inhomogeneities, there wouldn't be any galaxies. And so in this view, extraordinarily, the act of observing like even a big thing like a galaxy is in effect a quantum measurement process. And we live in a particular universe where the galaxies are in particular places because the quantum wave function has, for whatever reason, collapsed in such a way that the galaxy is in this position rather than in some other position where that galaxy could equally well have been. So what does that mean? Well, if we take randomness as a fundamental property of cosmology and of nature, this means that we can no longer try and predict exact properties of the universe, like the locations and sizes of every galaxy in the universe. We can only predict statistical quantities. And we already saw in the cosmic microwave background, my theoretical prediction was the power spectrum, which measures the typical size of fluctuations on a given scale, but doesn't predict the precise pattern of fluctuations. So you can learn about clustering properties, but not about individual locations. Now, this does have a serious limitation for cosmology, at least on the largest scales, that we have now imagining this ensemble of all the possible universes that might have existed, all of these different random outcomes that could have happened, but we just live in one universe, the universe that actually happened. And what that means is that we are probing every measurement we make is the measurement within a single member of the ensemble of possible universes that could have existed. And this gives the limitation to how accurately you can make your statistical inferences. And cosmologists call this cosmic variance, but it's really just a fancy form of sample variance. And you can see this in the power spectrum that I showed earlier. What you might remember here is for a spherical harmonic index L, which is the x-axis, in the spherical harmonic, for every L, you also have the M index that you use in quantum mechanics, and the M ranges from -L to +L. So for any given spherical harmonic L, you can measure 2L plus 1 independent quantities from the sky map that you have. So if I'm at L of 1,000, I have 2,001 independent measurements I can make. And each one of those measurements is a Gaussian random number. But if I average over all of those Gaussians, I can get a very accurate measurement. And that's what you see here in this plot. But on the largest scales, which is the left-hand side of the plot, say the quadrupole L equals 2, the quadrupole only has 5 independent modes, M running from -2, -1, 0, +1, +2. There are only 5 modes to average over, and that's not enough to completely eliminate the statistical noise. And you see the error bars on the largest scales are much bigger than they are than on the other scales. And this is a fundamental limit to what we can learn about the universe in its largest scales that can never be overcome because we're constrained to make measurements within our one universe. Okay, continuing to, I put a backdrop just because I'm going to move into more extravagant claims and ones which I'm less confident are correct. Quantum mechanics has many interpretations, and I wanted to mention briefly that there is the many worlds interpretation, which people seem to think is quite plausible. I have no opinion on that really. But in the many worlds interpretation, we have all these different possible universes that I've mentioned, with galaxies appearing in different places according to some clustering pattern. And in the many worlds interpretation, presumably all of these possible universes actually exist. They don't communicate with each other, they're just connected in some way, but it's the usual many worlds thing in quantum mechanics. I just wanted to say that as far as I could tell, but I may be wrong, it seems to me that the many worlds interpretation is essentially deterministic rather than random, because you have every possible thing arising. So you have complete predictability of all of these many worlds that might exist. So it's a little different from the Copenhagen interpretation, which is random, and you can't predict what's which universe you finish up in. Probably the many worlds is, however, time irreversible. I don't think anyone, since the different universes are disconnected from each other, how would you possibly bring them back together into some previous state? That doesn't seem possible to me. And still, how we're located within these many worlds is essentially a random thing. So the randomness is shifted from being the randomness of the actual universe, which is brought into existence by wave function collapse, into a randomness of where we're located in this maze of many worlds, which is illustrated by the graph in the background of this slide. Okay, I diverted in that direction of many worlds because I wanted also to briefly talk about another thing which muddies the cosmological waters a little bit, which is the possible existence of a multiverse. And this is something which causes a lot of controversy, including in my own household.
In this household?
In this household, Marina, who's right here, is very strongly opposed to the multiverse, and whereas I'm quite ambivalent about the multiverse. But what I want to say here is that the multiverse is a consequence of some of the models of inflation. it's known that this is possible since sometime in the 1990s. Yeah, Marina's always saying if we can't agree about the multiverse, we might finish up having to get divorced and become the world's first multiverse divorce. Let's see if we can reconcile that. And anyway, the multiverse means that you have variation in the properties, both the physical environment and perhaps even the nature of physical laws, varying from region to region in the universe on some enormous scale. When I say, one way to think about what I mean by nature of physical laws is that in our part of the universe, symmetries have broken and created the standard model of particle physics, which is based around a particular set of symmetry groups, SU3 cross SU2 cross U1. But it might be that in other regions of the universe, the symmetry breaking pattern was different, and the symmetries governing fundamental physical laws and interactions and particles in some distant part of the universe might be something completely different, the SU5 group or something completely different like that. So that's what I mean by variation of the nature of physical laws. Now, I do want to stress, I've been trying to be careful with the wording here. The multiverse is often criticized, and the way people criticize it is something along the lines of, I don't like the multiverse theory because I don't think it's falsifiable, because you can't go to these other universes and see what their properties are. That's misguided in my view, because the multiverse is not a theory. No one's suggesting that that's just a theory that there's a multiverse there. The multiverse is a consequence of some models, particularly simple models of inflation. And those models have been introduced for other reasons. In particular, they give precision descriptions of the cosmic microwave background, which is precision data, and you need these models of inflation in order to fit it. And once you've bought that you're going to use your model of inflation to predict the data you do have, the cosmic microwave background, you can't then ignore the fact that that theory simultaneously predicts the existence of a multiverse. And in particular, the existence of these models may be falsifiable for reasons other than the fact that they predict the existence of a multiverse. But we have to accept that many models which do describe observed properties of the universe simultaneously predict this multiverse property. Now, again, I want to encourage you to have the right view in your mind about what a multiverse might look like. When you see someone draw the multiverse, they tend to draw bubbles, either completely separate bubbles disconnected from each other, or they might have some kind of threads joining them, which could be viewed as wormholes. But I don't think that's really what inflation models predict. Inflation expands a small patch of the universe to become large, and at the same time allows for the possible variation of environment or physical laws. So I would say you want to think of a single very large manifold on which physical properties are varying. And again, I think it might be helpful to think of a computer screen. So in this case, you imagine there's some variation going across your computer screen, and this is on some absolutely colossal, enormous length scale. So I now think about an individual pixel on my computer screen, and within that pixel, physical properties are well fixed. They don't vary because the pixel is very small compared to this large scale variation. And then within that pixel, I have to suddenly imagine that that pixel is itself a computer screen. And I zoom into another pixel within that pixel. And our entire observable universe, everything we can see, might reside within that single pixel within a pixel. And then that observable universe itself, yet again, pixelize it. And our own galaxy lives within a single pixel of the pixel of the pixel. So it's all nested within itself, and the range of scales is absolutely colossal. And I think that, for me, is the best way to visualize what's going on. But any multiverse effect is happening on a scale that's enormously larger than anything that we can directly observe.
Sorry, Andrew?
Yes.
I'd like to notify you, there's 10 more minutes in total.
10 more minutes, that's perfect. That sounds great. Okay, so I wanted to pause briefly before launching into some implications of all this, is to say what could be what would make a satisfactory theoretical explanation of cosmology. So what I've said is that we have a very, very good observations, very accurate phenomenological modeling of these observations, but not very good fundamental physics understanding. Now, a theorist operates in the following way, that you like to start from principles. The idea is that we'd like to be able to state some number of principles that we like, which tell us is our view of how the universe operates. And the consequences of these principles are, of course, required to match what we actually observe in the universe. And so a good theoretical explanation combines principles with data. A good example is the standard model of particle physics, where we've decided that it's going to be a quantum field theory governed by some particular symmetries. We don't know what those symmetries are, but we go to CERN, make precision measurements, and we discover that a particular set of symmetry groups gives an excellent description of all the particle physics data that's ever been obtained. So this is the context of fundamental physics, and cosmologists work within the same context. So normally we believe that physical laws are invoked through symmetries. Our job is to decide what kinds of symmetries nature respects, such as the reparameterization invariance of general relativity, the gauge symmetries of quantum field theories, or some more complicated symmetries that might arise from a more fundamental structure like superstring theory or M theory or some other dynamics of extended objects. So in cosmology, the hope is presumably to write down some kind of effective field theory, which contains all of the information we need to describe the data. And to be satisfying and meaningful, what we need in cosmology is to find some way to tie that field theory to other parts of fundamental physics to create a unified whole. So we want, for example, we don't understand what dark matter is at the moment, but it's presumably part of some particle physics theory. Most likely the dark matter is comprised of individual fundamental particles. We'd like to see how that fits into other parts of fundamental physics, like the standard model of particle physics, and understand how that standard model is to be extended to the higher energies that we need in cosmology, and perhaps also to lower energies that we might also need to have a full cosmological description. So this kind of principle could, however, be realized in different ways, and I want us to think a little bit about different ways in which this might be realized. So I think of three main options, and option one is that if you're a very powerful theorist, you might have principles that are so strong that they actually select out a unique description of the universe, and that unique description might then be compatible with what we know about the universe and give a complete, rounded, ultimate description of how the universe works. Now, I think these days that sounds fairly absurd. Certainly when I say it, it sounds absurd to me. This is definitely what people thought in the 1980s when superstring theory first got underway. The first when people found the Green-Schwarz anomaly cancellation, started to believe there might only be one or maybe two kinds of superstring theory. Everyone seemed to believe that this was going to be a unique theory, and in a few weeks or a few months or a few years, we'd have a single comprehensive theory of everything. It was not just around the corner, and probably it never will be. This program has gone completely the opposite direction. So single consistent description is one option. Another option is that there are several consistent descriptions of the data we see, and one of which is observed, and we just have to assume maybe it's picked by chance. There's plenty of precedent for that. Here's an analogous question. Our solar system's got 8 planets. Why does it have 8 planets? I don't think that question has an actual answer. A possible answer is that solar systems usually have a few planets. Maybe they have planets ranging from 1 to 20 or more with some probability distribution. Our solar system just happens to have 8. I don't think there's any more fundamental reason than that. If we lived in a different solar system, I'm sure the number would be some different number to 8. So it could be that our universe is like that. There's lots of possible universes, and we just happen to be in one. Certainly, from a theoretical perspective, we have a version of this because we find there are many different ways of modeling cosmology that give rise to essentially the same observational outcome. In particular, there are different dark matter candidates, different models of inflation, that are being posited, our limit to distinguish these is quite limited. And in many cases, the models are perfectly degenerate. They give exactly the same predictions for what we can observe coming from different types of fundamental theory. And so there are questions we may never be able to answer using cosmological observations. We might also find that the answers to some questions, like the solar system example I've given, are just probability distributions. The answers are not precise numbers. All we can say is we can predict some probability and see whether or not the observed value is more or less consistent with what would be expected from that. Option 3 is, I think, a bit more interesting, which is there might be a colossal number of descriptions, very many consistent descriptions, and we might have to bring in extra reasoning to try and understand why our universe is like it is. And the example I've got here is another astronomy example, which is that we know that our moon is very large compared to the typical sizes of moons in the solar system. Even the giant planets, the moons are at most similar in size to our own moon. They're not in proportion to the size of the planet. Why is our moon so large? Now, one thing could just be to say, well, moons have a particular size and ours just happens to be large, which is my 8 planets version. But you can try and go deeper and ask whether there is a deeper explanation of why the moon is so large, and people have done that. And an example of such an explanation is to say that the large moon is necessary to stabilize the rotation of the host planet, and that might be a reason why the Earth is particularly suitable to life, because it's given a long-term stability to the climatic conditions on the Earth, which have made it easier for life to develop. And if you then take as read that we as observers are living things, there's a correlation between the properties of our environment and the ability of life to exist within that environment, which means that we would expect in planets that have life that the moons are typically larger than the average moon. And that's a probabilistic interpretation, but a very reasonable one, I think. And we find that this is echoed in modern superstring theory, because it's been discovered sometime again in the 1990s that rather than there being a unique superstring theory, the superstring theory has an enormous number of possible vacuum states. An estimate from a long time ago is that there are at least 10 to the 500 possible vacuum states of the universe, each corresponding to different nature of physical laws. And if you want to try and navigate yourself within this spectrum of possibilities, you might have to bring in extra types of reasoning, and particularly one of the kinds that gets brought into play is that only some very small subset of these 10 to the 500 possible universes appear to be amenable to having a long-lived universe in which life can develop. So you can have a strong correlation between the existence of life and the region of physical space in which you inhabit. Okay, I need to accelerate towards my conclusions. This is a little diversion to the limits of what we can know, which I think has already been said by various people in this conference. I don't really have to say it again. The limits to predictability come from different kinds. A lot of focus tends to go into the not knowing of initial conditions. So we saw the beautiful work on the triple black hole systems, for example, yesterday, that shows that if you don't know the initial conditions to exceedingly high precision, possibly sub-Planckian, then you can't make predictions. In cosmology, I think we're more concerned not with initial conditions, but with the validity of the equations we're using. We don't expect that the physical laws like general relativity necessarily apply to very small scales, which means high energies, or to very high precision measurements. I hope that disappearance of my screen doesn't mean the disappearance of the sound. Can you still hear me?
Yes, we can still hear you.
Okay, that's good. Another direction, which maybe hasn't been mentioned so far as limits to what we know, is that it may be the fault is not us for being inexact or our physical laws for being inexact, but that nature itself may be inexact. And I think this relates to the agenda of whether real numbers exist, to the possibility of space-time having a limiting discrete structure, that nature itself may be incapable of fully realizing the mathematical structures that we want to impose on it. Finally, I want to talk about information and relate back to some things that Mark was saying. This is my last topic. One of the ways we can try and understand the universe is to talk a bit about information and where the information content of the universe lies by considering the entropy budget of the universe. This has been worked on over the decades. And the current view of where the entropy in the universe lies is the following. Thermal entropy is actually very small. It's an absolute, it's a large number. In our observable universe, the entropy is 10 to the 90, and the number of degrees of freedom is the exponential of that. So 10 to the 10 to the 90 is a very large number, more or less just representing the number of photons in the observable universe. We've come to understand this is much smaller than other sources of entropy in the universe. In particular, the dominant material source of entropy in the universe is supermassive black holes, according to the entropy area law, the Bekenstein-Hawking formula. And if you evaluate the total amount of entropy in all of the supermassive black holes observed in the centers of galaxies, it's dominated by the most massive black holes because it scales as the area and hence as the mass squared of the black holes. The total entropy in all of the black holes is believed to be about 10 to the 104, so completely dwarfs the entropy in radiation. And nowadays, we also believe that there's a cosmic horizon caused by the dark energy accelerating the universe. And although this is a bit more controversial, the entropy associated with the cosmic horizon is about 10 to the power 124, completely dwarfs the entropy of the material sources. So the entropy budget is dominated by gravitational effects and not by thermal effects. And the number of states that the universe has is given by the exponential of this. And this gives us a way of counting the information in the universe by telling us what we have to specify to identify our universe amongst all the possible universes that might have existed. So our universe is 1 in 10 to the 10 to the 124 possible universes, according to this count. And that's the amount of information which is available. Now, what I've talked about is the standard kind of dead universe. In the next talk, Marina will also be discussing how biological systems might affect this information count. We've been working on this very hard for a few years. We call the topic biocosmology, and she'll be telling you about that just after my talk. But I'm sticking with the conventional cosmology, and I want to end by just raising a few questions about information which I find very puzzling and I think relates to determinism, indeterminism, in a way which I'm hoping that we will all understand better sometime in the near future. So a few comments on information. One is that the inflation process generates lots of entropy. The universe expands extremely rapidly when it's young, we believe, and it keeps the entropy per unit volume roughly constant. So the amount of entropy that's generated is absolutely colossal because you're generating lots more volume in which the entropy is the same. So inflation is an entropy generating process, but we, however, never get to see this entropy because it's all flung out to large scales and is outside our present observable universe. So that may not be very helpful. And what we finish up with is that the entropy of the universe after inflation is very, very small compared to the present, because the black holes and the cosmic horizon that dominate the present entropy budget are not present when the universe is very young. There's just the radiation that's there. And people like Roger Penrose and others have long highlighted that this means that the post-inflation initial condition is very special for having extremely low entropy. This might be useful in that it provides a possible origin of the arrow of thermodynamic time that tells the universe, it means the universe has plenty of scope to evolve to higher entropy states during its evolution. But it leaves the mystery of why that initial condition is such a special state rather than randomly chosen from all the possible states that you might have given by this much larger entropy. Another thing about information is that our normal thermodynamics ideas of entropy are defied by gravity, because gravity has a negative specific heat, and gravity attributes large entropies to collapsed states rather than uniform ones. And the black holes are the high entropy states rather than material being distributed uniformly. So all the things we normally learn in thermodynamics about entropy generally cease to apply once you bring gravity into play. And this is why people would once have thought, if you start with a thermal state in the cosmic microwave background, how can you get anything out of that? Because the thermal state is supposed to be the highest entropy state, so how can it evolve into anything else? And the answer, I think, is that gravity changes the rules, and gravity tells us there are much higher entropy states, which are non-uniform states. And gravity tries to lead us towards these states and have supermassive black holes form. So presumably the entropy in the universe has been jumped dramatically when supermassive black holes first formed, jumped again when cosmic acceleration started.
Sorry, one more
Yes.
minute.
One more minute. Okay. A big puzzle for me that comes from something Mark was saying is that if you consider a region which contains a galaxy, the information in the initial conditions are quite smooth. That's what inflation predicts. You don't have very small scale fluctuations. The initial conditions of the region that collapsed to form a galaxy is very, very small, even compared to the number of particles making up that galaxy. And this seems quite mysterious because you think with a galaxy, you could just position all the atoms wherever you liked, and it would just be a galaxy. All these are possible galaxies where the atoms are all swirling around in any old place. But it seems that that's not the case, and that the initial conditions have much less information than would be needed to let all these particles be wherever they want to be. So somehow the locations of all of the particles in the galaxies must be correlated in some way to each other. And if you knew the positions of just a small subset of them, you should be able to predict the positions of all the others based on the fact that those positions could only have come from some particular choice of the initial conditions in that region. And I find this question of the information and how the information might or might not change very puzzling at the moment. Mark certainly has very strong ideas along this, and I hope that this will be understood better. I'm still a little puzzled about whether the thermal variations that Mark mentioned might be somehow additional to the initial conditions, derivable from the initial conditions. Does the information develop as structure forms through these thermal variations? Very, very puzzling to me. Okay, last comment in my probably already past last minute is that I feel I have to comment on our own obvious indeterminism. Now, I'm a physicist, and physicists overall tend to be hardcore. We believe that physics is everything. So biology that affects us is just some form of chemistry. Chemistry is just some form of physics. So biology is just physics. This is what most physicists think, but it's not how physicists live. Nobody that I know, however hardcore they are, lives their life as if the future is already predetermined by the laws of physics or is going to be governed randomly by some quantum random decay process. Everyone acts in the belief that they can envisage possible futures, different things they might do, different places they might go on holiday, and that everyone believes that they, through their own choices, can make one of those possible things real. This, to me, is an obvious indeterminism in the way that we act and the way we believe. And some people disagree with this, and I find it's kind of almost entertaining. And you can find people who claim that free will is an illusion. We don't actually have free will, but somehow those people, they're always smug about it. They're always think, oh yeah, I'm really clever because I've realized that free will is just an illusion. But if they were logically consistent, they would then have to realize that they don't own their own beliefs. Their beliefs are a consequence of the determinism that they're invoking. And everything they've done or thought was already laid down long before they were even born. So you can't claim any credit for believing that free will is just an illusion. It makes no coherent sense to do so. So this is my question: where does this indeterminism come from? Now, physicists, a significant subset of physicists in condensed matter, believe there are emergent properties even in condensed matter physics, which are not predictable from fundamental physics. Living systems are much more complicated and non-ergodic than condensed matter systems, and biological systems are, in particular, seem to be subject to different kinds of explanations to the explanations that we have in physical laws, particularly functional explanations. A heart exists, of course, because the laws of physics permit the heart to exist, but you can't predict the existence of a heart in the universe by talking only about the laws of physics. Its existence is, hearts exist in our universe because they perform functions and that those functions can be acted upon by natural selection in order to create the heart. So this, to me, is the key question around indeterminism. The evolution of functions, biological states, is that the place where our own way to defy determinism lies? And that's where I'm finishing. Sorry for the small overrun. Thanks for your attention.
Thank you. I think we have time for maybe one or two brief questions.
Yeah, thank you, Andrew, for this quite fascinating talk. Okay, many questions, but maybe well, maybe one about this cosmic background radiation picture. Blue, I don't remember that. I think blue is where the radiation is a bit lower, red is higher. Exactly.
Yes, that's right.
So why is it that the majority of the picture is not white? Because it should be white because that's the center. And I see only blue and red region, almost no white regions.
Yes, yeah, I think that the color scale is very compressed in the center. So I think it is a little hard to see the dynamic resolution. And I would judge that the width of the distribution is a significant fraction of the color scale. And indeed, the pixels are known to very accurately follow a Gaussian distribution. So I think the difficulty of seeing the white is only that the white color is occupying only a very narrow part of the center of that Gaussian distribution. And most of the Gaussian is in the area which is various shades of blue and various shades of red. But yeah, I agree that it does look a little bit odd in those sense, because the very dark red and very dark blue seem to be quite prominent as well.
Okay, so this is an optical illusion. The other
I think
question is a very different
yeah.
sort. So at some point that by observing a galaxy, we produce I don't know, a measurement or a collapse due to a measurement. But I mean, of course, all that happened long before there was anyone able to observe a galaxy.
This is the fundamental question of the nature of quantum measurement. In absolute principle, it's hard to see how it would work with the galaxy, but at some point we point a telescope and observe a galaxy, and if you're the type of quantum theorist who believes that an observation requires, say, something like a human being to carry it out, then it could be the case that the first time that galaxy is observed is the time that that human being points the telescope. And in principle, if you're not a super determinist, you have to say in quantum theory that you've chosen to make a particular measurement, but you could have chosen to make a different measurement of some observable that does not commute with the one you have observed. So say the galaxy momentum in some sense rather than the galaxy position. And if you allow yourself that possibility of having chosen to measure different non-commuting observables, you're forced to believe that the wave function was not collapsed until the point you make the measurement, because you had to keep open the possibility you would have measured something different. Now, I think that is sort of classic Copenhagen interpretation view that the galaxy then does only miraculously spring into being at the instant of its observation. But to me, that sounds ridiculous. And I'm not sure it's any less ridiculous in a lab than it is in a cosmic context. So if something collapses the wave function, I think it must be something much less developed than an intelligent being making an observation with some kind of apparatus.
Yeah, indeed.
But in principle, it's the same. I don't think it's philosophically any different to what you do in a lab. It just seems ridiculous because you're applying it on a cosmic scale.
Okay, one more final question.
So can you hear me well?
Can you hear Tim?
Here, let me just unmute myself. No, let me
Okay,
not.
yes, I can hear.
Okay, let me do. So I go there.
No, I can make this.
Yeah.
Hello?
Okay, there we go. Now you can hear.
Okay, yes, I can hear.
So there, now we're getting an echo here. There are many questions, you raised a whole lot of issues, but let me just bring two really quickly. One is on the anthropic kind of reasoning that you talked about, the kind of explanation it gives.
Mhm.
I take it you agree if you ask, why do we have a large moon? That there are two steps to that, right? One is you want the cosmology to just tell you there are probably lots of planets with large moons, maybe a very small subset of planets, but some, and if the universe is large enough, therefore many. And then given that, you can say, why do we happen to live on one of the planets with large moons? And then this anthropic reasoning can come in and say, well, we couldn't have evolved or would have been unlikely to evolve on any other planet. That's a perfectly good explanation, but it, as it were, doesn't explain why there are planets with large moons in the first place, right? It's just
Yes,
targeted
that's
at
right.
a
You
different
need some
question.
theory
Um,
of the sizes of
and-
moons.
Well, I had a second thing I was going to say, but now I've knocked out of my mind giving the first one. Oh, yeah, no, I know what I wanted to say. This is just about what you were just saying. Of course, it doesn't make any sense to say, gee, these galaxies didn't actually have structures until people or mice or amoebas observe them. Because then the people or the mice or the amoebas already have to be there, right? I mean, they
Yes,
have to,
absolutely.
they have to exist to do the observing. And if there weren't pretty definite facts about what the galaxies were and the planets were and the, primordial seas on the planets
Mhm.
were, then there would never, and none of these things would have evolved. So that it's not just that it's just kind of completely incoherent to make the
Yes,
claim.
I agree. Yes, it's
Yeah,
asking
that
you
was
to
suggested.
observe yourself into existence somehow. It's, yeah, I completely agree.